Hacktivismo, and he's doing proactively secure programming techniques. I'll let you have it.
All right, thank you. Yes, as you mentioned, my name is Salvatore Testa from Hacktivismo. Hacktivismo is a human rights and technology group. It is a subdivision of the Cult of the Dead Cow. What we focus on, we're a special projects group. We focus on researching and implementing circumvention technology designed to defeat state-sponsored censorship of the internet. We have a major announcement coming up here at Hope tomorrow, 1 p.m. It's going to be in the unscheduled speaker track. We're promoting it heavily. Please show up. We're going to be releasing a major project tomorrow. One result of that project is this presentation. For the last 3.5 years, I've been working on this project, an unnamed project, and along the way, I've been thinking here and there little details about proactive programming techniques, and that's what I'd like to share with you today. First, a lot of the techniques deal with, in the context of direct memory languages, so let me define that first. Direct memory languages are those that allow direct access to memory without any bounds checking. Those are the older languages, assembly, C, C++. There's no bounds checking when you access arrays for reading or writing. It's just done directly in memory. So I guess non-direct memory languages will be those that allow access only if it falls within the buffer's range. So it has to do bounds checking every single time you read or write. Examples are the newer languages Java, PHP, Perl, Python, and others. Okay, so the first point I'd like to point out is don't use direct memory languages. There's little need to use them anymore. The newer languages such as Java, PHP, Perl that I just mentioned, those are better for several reasons. Faster development time, for one. And due to the bounds checking, they're immune to buffer overflows. Mostly, I mean, in the code that you write, you'll be immune to buffer overflows, but I remember there was one time in Java, the Java from Sun was vulnerable to a buffer overflow. But that is a problem in very specific code that can be fixed in one spot, not in thousands of projects. So the consequences of bounds checking, one, slower execution time. Every time you access an array, reading or writing, it has to be done, so that slows it down. The benefits, like I said, faster development time and immunity from buffer overflows. So that's why you shouldn't use them anymore. It is tempting to still use C and C++, okay? I'm a hardcore programmer. I like C. I like the power it gives you, but you have to fight that, okay? You have to fight that urge. Get it out of your system. Try to use these newer languages when you can. So the bottom line is, if you need to use these direct memory languages, use proactively secure programming techniques to prevent buffer overflows and other logic errors. So the question is, what is proactive? And that I'm talking about using, it's an application of defense in depth at the code level. It's an implementation, an actual instantiation of the defense in depth principle at the code level. I should give a quick buffer overflow example. This is by far a definitive guide on buffer overflows, but let's look at this program here. You have two variables, one called authenticated, which is an integer set to 0. You have a character buffer, which is 16 bytes long. Defined in that order, the GCC compiler will place buff in low memory and auth in high memory. I don't think that that is a requirement, a C, ANSI C requirement, but that seems to be pretty common with compilers to put variables defined later in low memory. So the program copies from the command line AV1 blindly into BUF, the buff 16-byte character array, and checks to see that buff is equal to password. If so, it sets authenticated to 1. Later we have some code that checks authenticated, and if it's non-zero, which is 1, it'll print supercalifragilistic, meaning you authenticated. Otherwise, it'll print nopers. So at the top, we run this program with the wrong password, and it'll say no. We run it with the right program, it'll say yes. And then, remember, we didn't do any bounds checking on the string copy into BUF. So if we put a whole bunch of characters on the command line, that'll be copied into BUF blindly. You do it once, we didn't add enough, it says nopers. We do a little bit more, and all of a sudden, we authenticated. And what happened in memory is illustrated in that picture right there. The X's started out in BUF, but they overflowed over in the next memory address, which was where authenticated was stored. The hex value for these X's is non-zero. Let me switch back. The hex value for those X's are non-zero, and so if authenticated is non-zero, you just authenticated. So the first way to prevent against this buffer overflow is to use the stir_n functions. That's stir_ncat, stir_ncopy. Those are the function definitions right there. Takes 3 arguments: destination, source, and a size. I maintain that these functions have some quirks to them because they're a little non-intuitive. If you use these all the time, you can use them safely, but there's little things here and there that make it difficult. For example, your third variable n refers to how many characters to copy from source. It has nothing to do with dest. So if you're trying to protect overflow in dest, the destination, that third argument, there's no correlation. So it's a little non-intuitive. It is possible to use correctly, but I maintain it is a little non-intuitive. Here's an example. 2 character arrays, 8 bytes each. Copy a string yo dude, which is 7 bytes long, into BUF. It'll be null terminated, which means it occupies the entire buffer. The next copy is copying AV1 into BUF2. And on the right is an illustration of what happens when we run it. We run it with 7 bytes of input. We print them both out, and that's exactly what you expect. Input more than 7, and look at what happens at buff2. We overwrote the null terminator, and BUF2 became coalesced with BUF1. This is a problem. Hold on. Yeah. A safer replacement would be the stir_l functions. They were introduced in OpenBSD 2.4. They have similar definitions as the stir_ncat, stir_lcopy functions, but they're safer in that they protect DST. They guarantee that no more than size bytes are written into DST, and furthermore, it guarantees that a null terminator is written into DST. As we saw before, it is possible to overwrite the null terminator. So this protects against that. This is safer to use, it's more intuitive. Unfortunately, it's not portable. I believe OpenBSD is the only system that it exists upon. I saw a shake, no. What's that?
I think the other BSDs.
The other BSDs include that? Okay, that makes sense. I don't believe that's on Linux. Yeah, so the moral of this story is if you're trying to write code for those platforms, emulate it. It is easy to emulate. I've emulated it myself. If you want my code, I'll give it to you. Just email me. Next, strings. Strings are aware of their size, so they automatically resize themselves as necessary, versus character arrays, which are just ranges of memory addresses that don't grow. They're set. Strings are aware of their size, so they resize themselves. Any Java programmers in here? Do we have any Java programmers? What, like 10 people? Okay. Yeah, you guys know how easy it is to manipulate strings. It is very, very simple. Versus people, have you then switched back to C and try to manipulate strings then? It's pain. That's all I can describe it as. The interface there is very nice and very polished. From the functional standpoint, strings are so much easier to use. And from the security standpoint, it's better because you don't have to worry about buffer overflows. The strings take care of themselves. You do have to worry about buffer overflows in the string library, but that is a set location of code, small, it's centralized, and it can be audited multiple times. And surprisingly, in the C language, you can use strings. How many people actually knew that? Nobody. You can. One popular implementation in C is from the G library. Here's an example of the interface. You have gstring new, which takes a set initial value, returns a G string. Okay, a couple people got that. Yeah, so when you want to keep appending to this string, you have gstring append printf, which just keeps, you use C formatters, and you can just dump all kinds of data in there, and it grows, and you don't need to worry about it. So it is possible. Take a look at the struct on the left. You have str, which is a character array, a dynamic character array. Len, which contains the current length. Allocated len, which is how large str is currently allocated. So when it gets too big, these functions on the right will reallocate str as necessary and do copying if needed and so on. Another technique, proactive technique, wasting space. The problem, common off-by-one errors and array manipulations can overwrite past the end of a buffer. To guard against that, you can declare your buffers slightly larger than you need. If you declare them, say, 1 word size or 2 word sizes, which are 4 bytes each, 4 bytes per word on the 32-bit architectures, then if you have a off by 1 error or off by 2, which are much more rare but still happen, you are safe. Off by 1 overflows are exploitable sometimes, and they are a big deal. Some compilers actually do this automatically. From GCC 3.0 and further, does this automatically. You'll notice if you disassemble any programs that you declare a buffer 16 bytes long and magically it's like 24 bytes when you disassemble. It's doing that on purpose. Not all compilers do this. Does anybody know if the Microsoft compiler does this? I don't know. I'm not a Windows programmer. Primarily, nobody knows. I'm not sure if it does that. It's not standard. So if you want if you want to do this on multiple platforms, you have to do this yourself. It's a pain, I'm not going to lie. It takes a certain amount of obsession to do this and patience. Next, variable reordering. The stack variables can be reordered so the impact of buffer overflows are minimized. Like I showed before, the compiler will arrange variables in a set way backwards in memory. The later variables are put in low memory, so certain variable types are overflowed more than others, character arrays. So if you put those in later memory, an off by one error is not going to overflow something more important like an integer or something like that. You can still overflow into the next memory address, but the impact is minimized. It's not a full solution, but the ProPolice stack in OpenBSD implements this, just as an example of this in action. You can implement this yourself with a program, a preprocessor program, or just use ProPolice. Also, this is tedious to do by hand. Next, pointer nullification. The problem here, freeing a dynamic memory allocation twice can corrupt the heap structure in a controllable way. This happened 4 years ago, I remember, in the Z library, which is a compression library used by a lot of projects. It's embedded sometimes statically. There was a vulnerability, a double free vulnerability, where free was called twice on the same pointer, which turned out to be exploitable, although I don't think details were ever released. From this, I learned if you nullify pointers immediately after you free them, this protects you from this class of vulnerability. And the reason for that is that ANSI defines free of a null pointer as having no effect. So if you use this macro myFree, which frees your pointer and then immediately sets it to null, calling myFreeX on the same pointer twice in a row has no effect. There is no security vulnerability that arises because of this. Once upon a time, I thought that using this macro would make your program invincible to double free vulnerabilities. Can anybody point out why that is not true? In the front.
Parentheses around the second X?
No.
myFree is declared as a string.
What's that?
myFree is declared as a string.
No. I'm not sure what you mean by that.
Declared as a string, you set it to null, and it then somehow becomes a string and you allow it.
Oh. Pointer copying. If a program copies pointers all over the place, you might just set a local pointer null, but not the owner of the variable still has a valid memory address. That one caught me by surprise. Comments. These can protect against buffer overflows or logic errors. A good software engineer knows that the code that they write will be maintained by multiple people. These people have differing skill sets, cognitive abilities, mental state, which includes motivation, mood, and alertness. Good comments will lower the chances a maintainer introduces security vulnerabilities. There's a heavy psychology component in team programming. You need to make it as simple as possible for someone to maintain. This is hard to do, to get into somebody's head and try to understand how will a beginner see this code and how will they misunderstand something, and then try to write code comments that demystify your original design techniques, your design methodology. That's hard to do, but I believe if you try hard enough, you will get this right. Next, simple code. can protect against buffer overflows and logic errors. Here's the winner of the 1985 International Obfuscated C Code Contest. That's the winner. I don't know what that single line does. There's a lot of pointer dereferencing. No, there's not too many. Well, yeah, there's some pointer arithmetic, I guess you can say. The bottom line is don't do pointer arithmetic because that gets you in a lot of trouble. You don't need to do that. Break it up into a couple lines with some good comments. That's easier to maintain. Some people are really like to write complex code. It makes them feel tough. You have to break out of that. It doesn't help the person maintaining it.
What does that do, actually?
What's that?
What does that do?
Question is, what does that do? Writing simple code?
No, what is that?
I don't know. I just went to the web page and grabbed something hideous. Variable initializations. If you initialize variables right after they're declaring them, this protects you because on the stack, your variables are uninitialized. In the sense that you don't know what they contain. They contain values that exist from previous function calls, which could be controlled by an attacker. So if you use an uninitialized variable, that could lead to your program being compromised. So always initializing your variables gives you some security benefit, but also a very bit more of a usability and what am I looking for? It helps. It's faster to program like that because your programs will fail fast if you use an uninitialized variable. It'll fail every single time consistently. Default failure can prevent logic errors. Let's say you are switching between states. You're maintaining some kind of state information. On the left, we're checking states between 1, 2, and 3. Notice that if it's not state 1 and state 2, we're just assuming state 3. A more proactive approach would be on the right. You check your 3 states and default to an error. This is similar to a whitelist. This is whitelisting. If you add states, your code on the left will break because you're assuming state 3 when you created a state 4. Or if the state variable itself becomes corrupt, that also leads to errors. And those are my references. I'll take any questions, if any. Yep.
Should I go up here?
Yes.
So what kind of vulnerabilities are you talking about? You just talking about someone just running a C program, or are you talking about like someone using this sort of website, or having C being how it handles it, or what are you talking about?
Any programs written in direct memory languages, so assembly, C, C++, that
Where you do like running root as like or something?
anything where you're handling input from an untrusted user
Oh, and you have like a database?
or a user of a different privilege.
So you have like a database?
That would be applicable, yes.
Oh. And so what other kinds of bad programming can get you in trouble besides like the obvious buffer overflows?
I'm sorry, could you rephrase?
What kinds of bad programming things that you can do besides buffer overflows that will get you in trouble?
That's a big question. There's many classes of code vulnerabilities, buffer overflows, double freeze like I talked about.
Is there a way to test, like, if someone's gonna run some kind of debugger on you, on your program, and try to find vulnerabilities in it?
I'm sure there are. That's beyond the scope of this presentation.
Oh, okay, that's all.
Any last questions? All right. Well, thank you. I also have